Hi dear students, this is the third part of the subject ME 206 fluid machinery, that is reciprocating pump. Due to the reciprocating motion of the plunger or piston, it will have an acceleration during the first half of the stroke and retardation in the later half of the stroke. We all know the working of the reciprocating pump. I have explained in the first part. So while the piston moving from left to right, that is during the suction stroke, initially the piston will be having an accelerative motion, but at the end of the stroke piston has to stop, so piston will be having a decelerative motion. Same thing will be there in the case of the delivery stroke also. Initially the piston will be having an accelerative motion, whereas at the end of the stroke piston has to stop, so the piston will be having a decelerative motion. That means during the suction stroke, when crank rotates from 0 degree to 90 degree, the piston will be moving with the acceleration. From 90 degree to 180 degree, piston will have the deceleration. Same thing in the next half also, that is from 180 degree to the half of the 360 degree we will have accelerative motion. From there to 360 degree we will have the deceleration. So this acceleration and deceleration of the piston will have same effect on the fluid flowing through the suction pipe as well as the delivery pipe. This effect will be transmitted to the flowing fluid also. So due to the inertia of this water, a pressure variation occurs inside the cylinder. In this topics, we are going to derive an expression for the pressure variation due to acceleration of the piston. Before going to the derivation, we have to assume an important thing, that is, let us assume that the length of the connecting rod is very large compared with the crank radius, so that we can consider the motion of the plunger or piston as a simple harmonic motion. If you are taking this assumption, then only we can use the equation for the simple harmonic motion, which will be used in this derivation. So now let omega is the angular velocity of the crank in radian per second, theta angular displacement of the crank, say from the commencement of the suction stroke in a time interval of t second. That is, theta is the angular displacement traversed by the crank with respect to the horizontal direction, which will be clear from the next figure. Okay, this is the figure. Here you can see, here you can see the piston, the theta degree is the angular displacement of the theta. Here you can see the theta is the angular displacement of the crank. So as the crank rotates through an angle theta, the piston will be moving backward with a linear distance x. You can see x marked here. The movement of the piston, linear movement of the piston with respect to the angular displacement of the crank theta is marked here. So along the diameter of the crank, you can see that distance x here also, because the stroke length will be equal to 2 times radius of the crank. So whatever linear displacement piston is having, that we can see along the diameter of the crank. So that x is marked somewhere here. This x and this x are both are same. Okay, now both these x are same. Now the piston has traversed a angular displacement theta, and the speed is omega radian per second. Now from the relation we know that angular displacement theta equal to omega into t. That is the general relation that we are using, theta equal to omega t. Now displacement of the plunger or piston will be x, as we have seen here. X is the displacement of the plunger or piston, that we can write in terms of the radius of the crank as r minus r cos theta. Going to the previous figure, here you can see this much distance is r, and this much distance in terms of this distance in terms of cos theta will be, if you consider the cos theta equal to adjacent by hypotenuse, that is this small distance divided by r. So r into cos theta will be this small distance, so total radius r minus this distance will give x. I think it is clear. So we can write the displacement of the piston in terms of radius of the crank as x is equal to r minus r cos theta. R is common, you can take it outside. That's equal to r into 1 minus cos theta. So x is equal to r into 1 minus cos theta. That is the equation for the displacement of the piston. So cos theta is actually omega t. So I am replacing that theta with omega t. So x is equal to r into 1 minus cos omega t. Why I am replacing that theta is I want to find out the velocity, then we will be differentiating the displacement with respect to time. So initially the theta is we have an equation of theta in terms of omega, in terms of time t as theta equal to omega t. So I have to replace that theta by omega t. Now we want to find the velocity of the piston, capital V. Note down that capital V. This is velocity of the piston. Velocity of the piston, capital V equal to dx by dt. Since x is the distance of the piston moved or displacement of the piston. So capital V is the velocity of the piston. V is equal to dx by dt. Now just to differentiate the above equation, that is dx by dt is nothing but d by dt of r into 1 minus cos omega t. Here r is going to be a constant. R is going to be a constant that we can keep outside. Now we want to differentiate the first term, that is 1, it is a constant, therefore the differential will be 0. The next term is minus cos omega t. If you differentiate cos omega t minus cos omega t, already a minus sign is there, cos omega t, the differential of the cos omega t is sin omega, minus of sin omega t. So that minus into minus will cancel, that will become a positive term. And again we have to differentiate omega t with respect to time, then you will get an omega. So the total will be v equal to dx by dt equal to omega into r into sin omega t. Okay, I think it is clear. Now we want to find the acceleration. We just now we have found out the velocity of the piston. So here we are having two system, that is one is the cylinder piston arrangement and other one is the suction or delivery pipe, whatever, say the suction pipe. Okay, now the total discharge will remain constant, it is going to be constant. So area into velocity at one system will be equal to area into velocity at the other side. So I am considering equating the area into velocity of the pipe, whether it is suction or delivery, whatever it may be, area into small velocity, small v, area into velocity will be equal to capital A into capital V. Capital A is the area of the cylinder, where small a and capital A are the areas of the pipe and cylinder respectively. This equation I have got is just by equating the discharge through the pipe will be equal to discharge within the cylinder. So area into small v equal to capital A into capital V. Now from that equation we can find out the velocity of the flow within the pipe. Initially the capital V was the velocity of flow within the cylinder or velocity of the piston. Now we have found out the small v quantity, that is nothing but the velocity of the flow of the fluid within the suction or delivery pipe. So small v equal to capital A by small a into omega, capital A divided by small a into capital V. Actually capital V is omega r sin omega t. On substituting we will get small v equal to a by a omega r sin omega t. Now we want to find the acceleration of the water in the pipe. We want to find the acceleration of the water in the pipe. Since I have already taken small a as the area of the cross section of the pipe, therefore I am taking a new term f as the acceleration symbol. So f is equal to nothing but dv by dt, acceleration of the flow of the water in the pipe. F is equal to dv by dt. So I want to differentiate the velocity term of the flow of the fluid through the pipe divided with respect to t, d small v by dt, that is equal to a by a is constant, omega r is again constant. I want to just differentiate that sin omega t term only. So sin omega, so omega t will have differentiating, will have an answer of cos omega t into omega. By differentiating omega t we will get a into omega. So totally a by a omega square r cos omega t will be the acceleration term. So now we have seen x is equal to displacement, x is equal to r into 1 minus cos theta, small v velocity of the flow within the pipe equal to a by a omega r sin theta, and acceleration equal to capital A by a omega square r cos theta. I have just replaced that omega t with respect to theta, that's all. Omega t equal to theta, therefore I have replaced back to theta term. Okay, now weight of the water in suction or delivery pipe equal to W into A into L. W is nothing but specific weight rho into G. So if you multiply specific weight with the volume, you will get the weight. Actually small a into L means area into length, that will give the total volume of the fluid within the pipe. So that is multiplied by specific volume, you will get the total weight. That is a general equation that we are studying in the fluid mechanics. So the weight of the water in the pipe will be W into A into L, where A is the A cross-sectional area of the pipe and L is the length. While considering the suction side, we can take L as length of the suction pipe, and during the delivery stroke, we can take L as length of the delivery pipe. Now let PA equal to pressure intensity to produce the acceleration F. Now since force is equal to mass into acceleration, P into PA into A. PA into A means pressure into area will give the force. So force is equal to, this side we want mass. Initially we are having an equation W into A into L for the weight. Weight divided by G will give the mass. So mass is W into A into L by G into acceleration is F. Therefore PA equal to W into, the small a will cancel both sides. So PA will be equal to W into L by G into F. That is the equation for the pressure intensity produced due to the acceleration. Now we want to, from the pressure we want to find the head. How we will find the head? P, general equation is P equal to rho gh, that H is the pressure head where P is the pressure. So P by rho g will give pressure head. So PA is the acceleration pressure. Now if we want to find the acceleration pressure head HA, then just divide PA divided by the rho g term. Rho g is W, specific weight. So HA equal to PA by rho g, that's equal to PA is nothing but W into L by G into F divided by rho g, that finally it will reduce to L by G into F. Okay, that is the that W and W cancel, L by G into F will remain. PA by W equal to L by G into F. So pressure head HA equal to L by G into F, but F is equal to A by A omega square R cos theta, that we have already derived. So acceleration pressure head HA equal to L by G into A by A into omega square R cos theta. This is the fundamental equation or general equation that we are using to find out the acceleration pressure head. This is applicable for both suction as well as the delivery side. If you want to apply this equation for the suction side, what you want to do is just replace L by LS. LS is nothing but length of the suction pipe, LS, and capital A by small a. That small a you replace by the area of the suction, cross-sectional area of the suction pipe. So LS by G, LS by G, A by AS omega square R cos theta. Similarly, if you want to find the acceleration pressure at the delivery side, HAD equal to LD by G, A by AD. I am replacing L by LD and small a by AD, corresponding the delivery side values. That's all. So it is clear that now from this equation, if you closely look upon this equation, what you can conclude is, it is clear that HA depends on the value of the cos theta. HA is directly proportional or depending on the value of the cos theta. So the HA value will be maximum when cos theta will be equal to 1. So this term cos theta term becomes 1, then only HA will have the maximum value. So HA max will be L by G A by A omega square R. Now cos theta equal to 0, when cos theta equal to 0, what happens is the HA term becomes 0. So cos theta equal to 1 means it is, the angle is 0 degree, either 0 degree or 180 degree if it is a suction side. So at the 0 degree, if theta equal to 0 degree, we will have HA maximum, and at 180 degree also HA will be maximum, but at 90 degree HA will be minimum or equal to 0. When theta equal to 0, HA equal to L by G A by A omega square R. When theta equal to 90 degree, HA equal to 0. When theta equal to 180 degree, HA equal to minus L by G A by A omega square R. You can see a minus sign there, because whatever HA we are getting at the starting of the stroke will be just opposite in sign that of the at the end of the stroke. So now we want to find suction and delivery separately. Now at suction pipe side, pressure head due to acceleration, HA is equal to, as I have already told, I have replaced that L by LS and A by AS. HA is equal to LS by G A by AS omega square R cos theta, where LS is the suction pipe length and AS is the suction pipe cross-sectional area. And at the delivery side, we have pressure head due to acceleration, HAD equal to LD by G A by AD omega square R cos theta, where LD is the length of the delivery pipe and AD is the cross-sectional area of the pipe. So based on this, all this equation that we have derived, we can